All right, so we are looking at section 410, page 299. Section 410, page 299. I know that we're going a little bit out of order here, but I think it's a good idea for us to understand what a definite integral is and the idea of finding the area under the curve and the limit of a summation and all of that type of thing before we see what an indefinite integral is. You know how with derivatives, you can have a numeric derivative or you can have a symbolic derivative. What I mean by that is, like, let's say that you're taking the derivative of x squared. You get 2x, right? That's a symbolic derivative. I get an equation. But if they say find the derivative of x squared when x equals 5, then I get a numeric answer, right? Because I take the symbolic derivative 2x and then I plug 5 in and I get an answer of 10. So just like with derivatives, sometimes you get an equation as your answer and sometimes you get a number as your answer. The same thing can be true with integrals. Integrals, today they're going to tell me, are called antiderivatives. Now, that makes sense if we think about it. We've kind of alluded to the fact already that a derivative and an integral are inverses of each other. They undo each other. But they formally tell me that here in section 410, that an antiderivative is an indefinite integral. An anti, like the opposite of, the undoing of. Okay, so the undoing of a derivative or the opposite of a derivative, an antiderivative, is going to be an indefinite integral. Okay, what do we mean by indefinite integral? Well, when I had a definite integral, it had an a and a b value, right? I was saying I am looking at the area under the curve from this precise value to this precise value for this definite area. If it's indefinite, then instead of going from A to B, I'm not going to have stipulations so that I won't get a number as my answer, I'll get an equation as my answer. So definite integral is the same idea as like a numeric derivative. Indefinite integral is the same idea as a symbolic derivative. I'm going to get an equation as my answer instead of just getting a specific number. And an indefinite integral in section 410 is what we're talking about with an antiderivative. All right, so they tell me in this section some formulas that we're going to use for indefinite integrals or for antiderivatives. I think we can figure some of those formulas out for ourselves. Okay, look at this chart that we have here. All right, we know that if you take the derivative of x cubed, you get 3x squared. If you take the derivative of x to the fourth, you get 4x cubed. If you take the derivative of x to the fifth, we get 5x to the fourth. What we want to look at today is, how do I go backwards? How do I undo that? How do I undo the derivative to work my way backwards to the antiderivative? All right. So let's look and see if we see any patterns. What's happening with the exponents when I go from the derivative back to the antiderivative? What happens? They go up by 1, right? When you take the derivative, you reduce your exponent by 1. So the inverse of that makes sense then that I should be increasing it by 1. When you take the derivative, like x to the third, okay, what do you do with that 3, other than you reduce it by 1? But what else do you do with it? You move it out in front and you multiply by it, right? So what's the reverse of multiplying? Dividing. So if you'll notice, if I've got 3x to the second, you've already told me I would have to increase this exponent by 1 to get back here. But what else would I have to do to get back here? I would have to divide by it, right? And so we've just discovered the power rule for antiderivatives. If you have x to the n, you're going to increase that exponent by 1, and then you're going to divide by that thing that you come up with, right? Just like with derivatives, we decrease by 1 and multiply. With antiderivatives, we increase by 1 and we divide. So they tell me there on 299 that when I'm working with antiderivatives, something else that I need to kind of discover or play around with is the idea of, what is the derivative of x to the third? 3x squared. What's the derivative of x cubed minus 6?
3x squared.
3x squared. What's the derivative of x cubed plus 63,024?
3x squared.
So bottom line is, if you took the derivative of x cubed plus any constant on the face of the earth, what would you get? 3x squared. So for that reason, something else we're going to need to contend with is when I try to go backwards using my antiderivative, using this power rule that we were looking at up here, we are going to need to tack on plus c every single time we do an indefinite integral. It's called the arbitrary constant. And the reason for that is, as we just saw, c might be 0, or it might be -6, or it might be 63,024. But there is some constant there, even if it's 0, where it drops out. So when I do an indefinite integral, on page 299, they tell me a function is called an antiderivative if you can integrate the derivative and go back to the original function. So if you integrate, take the indefinite integral of a derivative, they're inverses of each other. They undo each other. They cancel each other out. The indefinite integral, or the antiderivative of a derivative, drops out and takes you back to your original function. Then, from what we just saw a second ago, of course, we need to leave that plus c on there to take into account any constant that we might have had. It's not a problem, because even if that constant was 0, it'll drop out, and so it won't skew my final answer in any way. Now, this notation is very natural for us. This is what we use for derivative. This is what we use for original function. So we will use this notation a lot of time, and the book does as well. But there's also an additional notation that the book uses. Sometimes they'll use lowercase f of x for derivative and uppercase f of x for antiderivative. But when they do, they're very clear about it. They'll say, capital F of x is the antiderivative of lowercase f of x. So you have no doubt what they're talking about. So they'll use that notation interchangeably. Okay, so we've already talked about this first rule up here, but here's how we can come up with our antiderivative formulas. If you had a constant times f of x, if you took the derivative of that, you would have that constant out in front times the derivative. So if you want the antiderivative of this, you just go back to where you started. All right, here's another one. If you took the derivative of sine, you would get cosine. So the antiderivative of cosine is sine. We're just undoing the formulas that we already know. In that case, I don't have to learn new ones. All right. If I want the antiderivative of sine, I have to add on something here. Because the derivative of cosine is negative sine, I don't want the derivative of negative sine. I want the derivative of positive sine. So I'd have to think of it as the derivative of negative cosine is sine. So the antiderivative of sine is negative cosine. Come down to tangent. The derivative of tangent is secant squared. So the antiderivative of secant squared is tangent. The derivative of secant is secant tangent. So the antiderivative of secant tangent is secant. So again, I get to use the formulas that I already know. I'm just kind of going backwards with them. Now, for the first little while we're doing this, your brain is going to spin in circles, because when you see x to the third, you're automatically going to do 3x squared. You're not going to be adding and dividing. You're going to be subtracting and multiplying. It's just by habit, okay? And so we'll work on antiderivatives for a good while to kind of lock those into our mind. And then about a month before the AP exam review, we will start doing derivatives and integrals on the same problems. They'll give me an equation, I'll take the derivative of it, and then I will integrate it so that I get used to putting those ideas together. And then, of course, for the whole time we're doing the AP exam review, we'll be doing both of those at the same time. So for right now, we're going to focus primarily on our integration and kind of cementing that into our mind, but we will go back to working on both of them simultaneously. Okay? All right, so look at example number 1. For example number 1, they say your derivative is x to the negative 3. So let's find the antiderivative, the original equation f of x. Okay, so what do we do to the negative 3? Add 1 to it, right? And then what do we divide by? That same number after I added the 1. Remember, my formula is n plus 1 in the exponent and in the denominator. So I'm going to add 1 to the negative 3 to get negative 2, and then I'm going to divide by that exact same number. And then I don't want to forget my arbitrary constant plus c. Now, a couple of different ways you could write that answer. So if they write it a little differently in the back of the book than you do, don't think you're doing it wrong. We could write it several different ways here. All right, look at example number 2. Now, all of the properties that we have already learned for definite integrals will apply to indefinite integrals in terms of, we've learned that if you have the integration of two things that are being subtracted, you can break that into two separate pieces and integrate each piece separately. If you have the integration of two things that are being added, you can take that one piece at a time and do the integration on each. If you have a constant out in front of a function, you can just integrate the function and then go back and work with that constant. So those properties that we learned in Chapter 5 will apply here as well. So let's start with this first piece right here, 4 sine x. I'm going to ignore the 4, and I'm just going to focus on sine x. What is the antiderivative of sine x? Negative cosine x, right. So then I'm going to put my 4 back in front after I've dealt with the function. Then I can just reintroduce the constant. All right, how about negative 3x to the 5th? What am I doing with that 5? Adding 1, right. So it'll be 6, and then I divide by that same number. All right, for the last piece, I'm going to ignore the constant of 6, and I'm just going to focus on the 4th root of x to the 3rd. I'm going to rewrite that as x to the 3/4 so that I can use my power rule for that. So if I add 1, what am I going to get?
1 3/4, 7/4.
X to the 7/4, right. So I'm going to have x to the 7/4 divided by that same number, 7/4. And then don't forget your arbitrary constant, your plus c at the end. All right, so I'm going to go back and do a little bit of simplifying. You actually may have done this simplifying while you were going through, but I'm going to do 4 times negative 1 is negative 4. 3 divided by 6 is 1/2. Dividing by 7/4 is the same thing as multiplying by 4/7. And then 6 times 4/7 will give me 24/7. Now, you definitely could, skip this step right here and not write this as a separate line and, just go to your last line. But I didn't want to lose anybody in, where did that 24/7 come from? All right, look at page 300 and, let me get there, 301. It says, in applications of calculus, it's very common to have a situation like we just had in example number 2, where it's required to find a function given knowledge about its derivative. An equation that involves the derivatives of a function is called differential equations. You may have looked ahead at some college courses and seen you have calculus 1, calculus 2, and then differential equations. A lot of times cal 3 is differential equations. For the present, we can solve some very elementary differential equations. The general solution of a differential equation has an arbitrary constant in it, like we just saw in example number 2. But sometimes they'll give me extra information where they might give me like an extra condition that enables me to find that arbitrary constant and eliminate it so that I can have an exact value and not have that arbitrary constant. That's what happens in example number 3. Let me show you what I'm talking about. For example 3, we've got the derivative is equal to x square roots of x, and f of 1 is equal to 2. So that's some information about the original function, right? We'll come back to that at the end. Let's just focus on this idea of the derivative is equal to x square roots of x. They want me to go back to f of x, the original function. At this point, I don't have a product rule. I don't have a quotient rule. I don't have a chain rule. I don't have hardly anything. I mean, literally all I have are the about 10 formulas that they've given me so far for shortcuts in integration. All right? So I've got to have some way that I can rewrite this without using a product. What could I do?
X to the 3/2.
Yeah, x to the 3/2. I could make it x times x to the 1/2 because the square root of x is x to the 1/2. And when your bases are the same and you're multiplying, you add your exponents. So 1 plus 1/2 is 3/2. So if this were an indefinite integral, I could then go through and say, okay, let's use power rule. I'm going to take 3 halves and add 1 to that. That would be 5 halves. And I'm going to divide by that same number, and I'm going to tack on my arbitrary constant. And then, of course, dividing by 5 halves is the same thing as multiplying by 2/5. After you do several of those, you're going to get to the point that you skip straight from this step to this step. Like in your head, instead of dividing by 5 halves, you're going to go ahead and flip that and say multiplying by 2/5. If you can do that right now, fantastic. If you need to write this extra step in for the first week while we're doing this, do that. Whatever you need to do to make yourself comfortable. All right, so this is our indefinite integral, our antiderivative, and I would be done except for the fact that they gave me some extra information on this problem. They will not always do that, but on this one, they told me f of 1 is equal to 2. So this is f of x, right? So that means if I put 1 in place of x, I know the answer would be 2. So I'm going to go back and I'm going to put 1 in the place of x, put 1 in the place of x, and I know when I'm done my answer will be 2. The nice thing about that is my only unknown is c. I'll be able to solve for c and get rid of that arbitrary constant and come up with a specific equation here.
So how do you know you just have like c isn't there and that's how you get your 2?
No, they told me that when I plug 1 in the place of x that my y value will be 2.
Oh, so you're trying to find c. Okay.
So we plugged 1 in for x right there. We still have our c there, but then we've set the final equation equal to 2 and we can solve for c. All right, so 1 to the 5 halves would give me 1, and then times 2/5 would just give me 2/5. So I've got 2/5 plus c is equal to 2. I'm going to subtract that 2/5 over to the other side, so 2 minus 2/5 gives me 8/5. So if c is equal to 8/5, I can come up and put that in the place of c, and I no longer have an arbitrary constant, right? I solved for that arbitrary constant and was able to fill it in. So I was able to find my unknown. Again, I only could do that because they gave me that extra piece of information in the beginning. All right, example 4, the same idea, but for example number 4, they start off with the second derivative, and they say the second derivative is equal to 12x squared plus 6x minus 4. F of 0 equals 4, f of 1 equals 1, so they've given me extra information I'll be able to use. And they want me to go back to the original equation, f of x. All right, how do I get rid of 2 derivatives?
You gotta add twice.
I got to do 2 antiderivatives, right? All right, so let's do the first antiderivative. So antiderivative of 12x squared.
12x to the third divided by 3.
12x to the third divided by 3. All right, how about 6x to the first? Yeah, you're both right. 6x to the second divided by 2, which would go down to 3x squared. All right, now look at this next one here. What is, we've got a negative 4. That would be negative 4x to the what? 0. X to the 0 is 1, right? So if I just have a negative 4 sitting there, there's an x to the 0 after it. So if I increase that by 1, I'm going to have x to the 1 over 1. So something that we'll see is that anytime you integrate a constant, you're going to get that constant times your variable. That should sound remarkably familiar. Remember the summation formula that we had? That was if you do the summation of a constant, it's that constant times n. Same kind of idea. And then, of course, we've got our plus c down here at the end. Okay, so to go back to the original function, you told me I would need to do that process twice. So we're going to have to go back and do that again. I'm going to simplify a little bit first before I do that. So 12 divided by 3 would be 4. 6 divided by 2 would be 3. 4 divided by 1 would be 4. All right, so if we take the antiderivative of 4x to the third, what are we going to get? X to the fourth. Right, now I'm going to do this in 2 steps so I don't lose anybody. I'm going to go ahead and add 1 and divide by that same number. But as you're doing this, if you can in your head go ahead and drop out those 4s and just write it as x to the fourth, that's wonderful. You'll just save yourself an extra line of writing, but you do what you need to do. All right, how about 3x squared? What are we going to get?
3x cubed divided by 3.
3x cubed divided by 3. How about 4x?
4x squared.
4x squared divided by 2. C is a constant. What did we just say if you integrated a constant, what would you get? That constant times the variable, right. So I have C. It represents a constant, so I'm going to get that constant times the variable. And then there is going to be an arbitrary constant for this integration as well. I can't use c because c could be 5, and the arbitrary constant doesn't have to be 5. It could be any number. So they use d here. Sometimes they'll use c1 and c2, like c with a subscript of 1 and c with a subscript of 2. Just some way to differentiate between the two of them is fine. And then again, I could simplify that a little bit. 4 divided by 4 is 1, 3 divided by 3 is 1, 4 divided by 2 is 1, c divided by 1 is c. Sorry, 4 divided by 2 is 2. No. Okay, so now that we've got our f of x, now we can go back and use that initial information that they gave us up here at the top. If they had not given us that extra information, I'm done. This is my antiderivative. But because they've given me extra things that I can use, let's start with f of 0 is equal to 4. That means that if I put 0 in the place of x, my answer when I'm done should be 4. So I can go through and say 0 to the 4th, 0 to the 3rd, negative 2 times 0 to the 2nd, c times 0 plus d is equal to 4. And when I solve that, I just end up with d is equal to 4. So I can put 4 in the place of this d right here, and here's my new equation. Here's what I know. I have x to the 4th plus x cubed minus 2x squared. Still have a c in there, cx plus 4. But they gave me a second piece of information. The second piece of information was that f of 1 is equal to 1. So now I'm going to go back and I'm going to put 1 in the place of x, and they've told me that when I do that, my answer should be 1. So if I put 1 in the place of x, I'll have 1 to the 4th, 1 to the 3rd, negative 2 times 1 squared plus c times 1 plus 4 is equal to 1. So 1 and 1 is 2, minus 2 is 0. So I'll just have c plus 4 equals 1. So to get c by itself, I'm going to subtract that 4 from both sides, and I'll get c equals negative 3. So if c equals negative 3, let's take that negative 3 and put it in the place of that c right there, and we'll end up with f of x is equal to x to the 4th plus x cubed minus 2x squared minus 3x plus 4. That is our original equation. And again, I could not go back to that original and get rid of c and d if they had not given me those extra pieces of information. All right, now over on page 303, they talk to us about rectilinear motion. It says antidifferentiation is particularly useful in analyzing the motion of an object moving in a straight line. Remember particle motion? Recall that if the object has a position function s equals f of t, the velocity is the first derivative and acceleration is the second derivative. So here's what happens in example 7. We're going to come back to 5 and 6 in a second, but this is so much like what we were just doing. I want to go to this next, okay? They tell me acceleration is equal to 6t plus 4. Work your way back to the original function. How do I get back to the original function? Antiderivative twice, right? Because acceleration is the second derivative. To get back to the original, just like we did in that last example, I'm going to need to work my way backwards twice. So, what is velocity in relation to the acceleration?
Velocity is the antiderivative of acceleration.
Nice. Velocity is the antiderivative of acceleration. If acceleration is the derivative of velocity, then the antiderivative of acceleration would be velocity, right? Okay, so we could go through then, and we're going to find velocity by doing the antiderivative. So 6t to the first is going to become 6t to the second divided by 2. 4, our constant, is going to become 4 times the variable, in this case t, and then don't forget your arbitrary constant. And a little bit of simplifying, 6 divided by 2 is 3. Now, they have given me some initial information again, or some extra information that they don't always give me. Notice that this time they gave me information about the velocity and about the position function. In that last example that we didn't have any information about the first derivative. We only had information about the final answer, right? So if right now I have information about the velocity, instead of continuing with a c, if I could get rid of that and continue on with a regular number, that's my preference. You can continue with the c and then just wait until you get to the very end to plug this stuff back in. But I'm going to go ahead and plug in what I know. I know that when I plug 0 into the velocity equation, I get negative 6. So I'm going to put 0 in the place of t in that velocity equation, and my answer will be negative 6. So that means that c has to be -6. So let's put that there. And now I've got a velocity equation that doesn't have an arbitrary constant. That's just me personally. That's my preference. All right, now how do I get back to position function? Antiderivative, right. So antiderivative of 3t squared, 3t cubed divided by 3, antiderivative of 4t, 4t squared divided by 2, and antiderivative of -6, -6t. And then don't forget your arbitrary constant. Again, I gave it a different letter this time. And a little bit simplifying, 3 divided by 3 is 1, 4 divided by 2 is 2. All right, so the other piece of initial information that they gave me was that s of 0 is equal to 9. So now that I have my s equation, if I put 0 in the place of t, my final answer will be equal to 9. So let's do that. 0 cubed, 2 times 0 squared, 6 times 0 plus d equals 9. So I'll get 0 plus d equals 9, so d equals 9. So let's put that right there. And now I have my original position function. All right, let's go back over to page 302. They talked to us about the geometry of antiderivatives. Basically, we want to look at what do the graphs of these look like. Now, we have worked with graphing original functions and derivatives in the past, but we've been going the opposite way. Like, they gave me the original function, and they asked me to graph the derivative, okay? So remember the way that we would do that. If we had the original function and we were trying to come up with the graph of the derivative, we would choose a point. Like let's say right here, we would draw a horizontal line and go, ooh, that has a slope of 0. And remember the slope here was the y value over here, right? So let's use that same idea. The slope of the antiderivative, the original function, is the y value of the derivative. The slope of the antiderivative, the original function, is the y value of the derivative. That's how we took an original function and graphed the derivative. Remember, we would draw horizontal lines everywhere we could, and then we would go back and we would figure out where we had positive slopes and where we had negative slopes, and whatever the slope was here was the y value over here. Now we want to go the opposite way. They are going to give me the graph of the derivative, and they are going to want me to create the graph of the antiderivative, the original function. So example 5, it says the graph of f is given. Make a rough sketch of the antiderivative, capital F, and then they give me one piece of information that capital F of 0 is equal to 2. So we'll be able to utilize that. If we come over here, we're trying to graph the original or the antiderivative. They gave me a starting point that I have the point 0, 2. Okay? Now I need to figure out what's going on at 1. So if I want to figure out the y value of this derivative, I'm going to come over here to that same point, x equals 1, and I'm going to figure out what's my slope. So I could say the y value of my derivative is going to be the slope of my antiderivative. So I can say, okay, right here I have the ordered pair 1, 0. That means at 1, I have a y value of 0. So that means over here at 1, I have a slope of 0. So I'm just going to draw in a slope at 0. All right, then I'm going to pull another ordered pair. I'm going to come over here and say, okay, I've got the ordered pair 2, 1. So that means that at 2, over here I'm going to have a slope of 1. So I'll come over here to x is equal to 2, and I'll draw myself a slope of 1. All right, then I'll get another point. At 3, I have a y value of 0. So I can come over here to x equals 3 and draw a y value of 0. And I'm going to keep going with that same process as many points as I need. So if I did not have this red graph on here, and I was told to graph the original or the antiderivative, I have a starting point, and then I can say, okay, I know I'm going to come down and this is going to level out here, so that's going to be where this has a minimum or where it bottoms out. And I know that up here is where it's going to have a maximum, it tops out. Okay, how do I know how to draw the line between those two? Well, I use this slope right here as a guide. So that lets me see the steepness for that line in between them. And then as I come away from this maximum here, how do I know how steep to make my line? Well, I use this guy as a guide for my slope, and I can keep going as far as I need to. Right? So that's one way that I can graph the original or the antiderivative when I'm given the derivative. The second way is by using something called a slope field or a direction field. And so example number 6, it says if f of x is equal to the square root of 1 plus x cubed minus x, sketch the graph of the antiderivative capital F that satisfies this initial condition. Okay, what do I need? I need ordered pairs. Remember up here, I needed ordered pairs, so I was looking at the graph to get them. Well, down here I don't have a graph, I have an equation. Okay, I'm going to get my ordered pairs from my equation because I'm going to plug the x values into the equation and get y values. So that's where all these points came from right here. I took and I plugged -1 into this equation. So -1 squared is 1. Square root of 1 plus 1 would be square root of 2. Plugged in -1. That's cubed. Sorry, can't read my own writing. Sorry. So -1 cubed is -1. 1 plus -1 is 0 squared is 0 is 0, minus a -1 is +1. Okay? Then I can plug in 0. So 1 plus 0 is 1, square root of 1 is 1. 1 minus 0 gives me 1. You get the idea. Okay? So all I've done to get ordered pairs is just plug into the equation. So if they give me an equation, I'll get the values from there. If they give me a graph, I'll get the values from there. Now, the reason this is called a slope field or a direction field is when I start over here with -1, 1, I can say, okay, I know that the slope of my antiderivative is the y value of my derivative. The y value is 1, so that means that at -1, I'm going to have a slope of 1 when I graph this thing. So I'm going to come over here to -1, and I'm going to graph a slope of 1. Now, this graph is there in your book, so you don't have to worry about trying to generate this, because it would take too long to draw right now. A slope of 1, I'm going to just draw a rise and a run that are equivalent to each other and use that as a guide for me to be able to estimate what a slope of 1 would look like. All right? Then I come over here and say, okay, when my x value is 0, my y value is 1, so that means at 0, again, I'm going to have a slope of 1. Then at 1, I had a y value of 0.4, so that means here at 1, I'm going to have a slope of 0.4. How do I draw a graph of 0.4? Well, 4/10 reduces to 2/5, so that's like rise 2, run 5. So if I kind of plot that out, then I can see how flat to make this line. All right, then at 2, I was back to a slope of 1 again, so I'm back to using this guide again for the steepness of these lines. At 3, I'm at 2.3. 2.3 is like 2 1/3, right? So I'm going to rise 2 1/3, and I'm going to run 1. That gives me my steepness. So again, that just kind of gives me a guide to follow. So what I've created for myself is a field that tells me what direction to go, made up of slopes. So that's why it's called a slope field or a direction field. So if I start at the point they gave me, they told me that f of -1 is equal to 0. So I'm going to come over here at -1, 0. Then I'm literally just going to follow that field that I've made out for myself. So I can say, okay, I'm going to follow the length of this line, and I'm going to come up here, and it's still that same slope. But as I approach here, it's a little flatter. And then as I come over here, it's going to be a little steeper again, and then as I come over here, it's going to be really steep. So you either can connect these little lines or you can run in between the lines. It kind of depends on how you have them drawn. If there's one right there waiting for you, you can just connect it. But if not, you can run in between two of them that you have drawn. But that will give you another way of sketching what the antiderivative or the original function would look like. Okay, so here is our homework for tonight on pages 304, 305. We're doing 1 through 25, every other odd, 31, 41, 47, 51, 55, challenge 45.